What would the world look like with a computer that could accurately model the laws of nature? That's the promise of quantum computing, but there have always been limitations. Now, as one of our longest running research projects, our team at Microsoft has been able to take a subatomic particle that has only been theorized until now, and not only observe it, but control it, creating an entirely new material and a new architecture for quantum computing. One that can scale to millions of qubits on a single chip.
This is not a work of science, it's a work of science and art.
I gotta be honest, some of these ideas are a little science fiction sounding.
It will solve problems unsolvable by the combined power of all the world's compute today, and promises to revolutionize fields such as medicine, material science, and our understanding of the natural world. Our first quantum processor based on this architecture is the Majorana 1. Yeah, I've always been fascinated with puzzles and challenges and a mixture of mathematics and computers. And so when I learned that there was this type of computer that didn't exist yet, but could solve problems that we couldn't solve with our digital, all of the computers we had, I was just fascinated. I wanted to learn, well, how can I help that computer be built? The number 30, 40, 50 electrons, those numbers are seemingly small, but require up to lifetime in the universe timescales to solve with all of the world's computers operating together. That's until you have a scaled quantum computer that can solve these problems efficiently. At the core of a quantum computer are these qubits. Qubits are like our classical bits, right? These are essentially zeros and ones in a transistor. And we need the analog of that in quantum computing. The analog is a qubit, a quantum bit, that serves as that core information unit. It's where we store the information and then we process on those qubits to create computation and ultimately, get solutions back out. Now, there's many different ways, right, to create a qubit. The reason quantum computing has been so slow to progress is that the industry has been struggling with problems making qubits reliable and resistant to noise. Progress has been incremental.
People in the early days of computation used vacuum tubes, and then that technology, actually, you could build very good computers with it, and then the transistor was invented, and the earliest transistors weren't necessarily that great, but it became clearer over time as the transistor developed and the integrated circuit developed that this was going to be the technology of the future. In that spirit that, the first generation of qubits may not be what gets us to the next stage where we can really solve the kind of problems I was mentioning that are really important. And so we might need to invent a material and therefore a quantum processing unit that has the right properties. So for us, we want something that has some built-in level of error protection. And a lot of those ideas actually were explored in the context of software, of quantum error correcting codes, but you can actually build a lot of those ideas into hardware.
So the way you design that qubit matters. We see the states of matter every day. Solids keep their shape, liquids vary but keep their volume, gases expand to fill the space they're in, all defined ultimately by how their atoms behave. But what if there were more? What if, under the right conditions, you could engineer more? States that have only ever been theorized, that would change how subatomic particles actually behave? 100 years ago, mathematicians predicted one such new state of matter, the topological state. And since then, researchers have been looking for a very specific, very useful quasi-particle within it, the Majorana particle. Last year, we were able to observe it for the first time. And this year, we're able to control it and use its unique properties to build a topoconductor, a new type of semiconductor that operates also as a superconductor. With this material, we can build a whole new foundational architecture for our quantum computers, a topological core, allowing us to scale to not tens or hundreds of qubits on a chip, but millions, all in the palm of your hand. So it really has taken quite some thinking, right? Some time to design a device, design a chip that can enable measurement of this literally elusive particle. We've designed a chip that is able to measure the presence of Majorana. Majorana allows us to create a topological qubit. A topological qubit is reliable, small, and controllable. This solves the noise problem that creates errors in qubits. Now that we have these topological qubits, we're able to build an entirely new quantum architecture, the topological core, which can scale to 1 million topological qubits on a tiny chip. Look at the design of this chip, right? First of all, you can fit so much on just a small form factor, right? This chip can store over 1 million qubits, right? Over 1 million can fit on just this small form factor. In addition, we don't want to wait centuries or millennia for a solution. And so this chip also offers the right speed to get solutions from the chip in a reasonable, efficient, amount of time. That's the beauty in this qubit design, the topological qubit. It has the right size, the right speed, and the right type of controllability. And all of that together means that it has an ability to scale like no other. What can you do with 1 million qubits? In the last few years, there's an explosion of artificial intelligence, right? Co-pilots. And what's so inspiring about a quantum computer is that with a quantum computer augmenting the AI capability, it can help drive even more discovery.
After 17 years, when we are showcasing our results, we are showcasing results that are not just incredible, they're real.
We're at the cusp of a quantum age, and Majorana 1 is just the beginning.